Welcome back to ME 760, Engineering Analysis 1. So last time we started the new chapter, chapter number 10, and it was all about the linear vector spaces and matrices. So last time we discussed what we mean by linear vector spaces, and we will continue today some of the properties of the dot product, for example, or inner products. So the properties of inner product. So inner product can be defined for linear vector spaces. Last time when we stated, or we talked about linear vector spaces, I stated that if you have n-dimensional vector space, it can, from the abstraction point of view, the components of the vector space or the objects of the vector space might be vectors, might be functions, might be matrices. So it's an abstraction. So let's say A, vector A, B, C, D. A may be a matrix, maybe a function, maybe a differential equation, maybe any abstraction. So here we will have, we'll define the dot product or the inner product of two vectors, vector A and vector B. And vector A and B belongs to linear vector space V, for example. So AB is just, let me give you the definition first before we go to the properties. So the definition is just AB. Sometimes we write it A, B, and sometimes we write it A, B. For three-dimensional vector space, you knew what's A dot B. A dot B is the amplitude of A multiplied by the amplitude of B multiplied by the cosine of the theta, the angle between the two vectors. So for real three-dimension vector space, if we are talking about three-dimensional vector space, A dot B is nothing more than A, amplitude of A multiplied by amplitude of B multiplied by cosine theta. And let's assume that this is vector A, this is vector B, and this is the angle theta between A and B. So there are certain properties for the inner product in n-dimensional vector space. Those properties are: one, A, the inner product of A and B is equal to B, A, and this is the complex conjugate. So this asterisk from now on will denote complex conjugate. You knew what's complex conjugate. So if you have A plus BJ, it's a complex number. What's the complex conjugate? So this is, let's assume that this is Z. This will be the Z star. Okay? So this is one of the properties. The other property is if we have the inner product of vector A with a scalar lambda multiplied by a vector B plus a scalar mu multiplied by a vector C. So this will be simply A dotted with B, or the inner product of A lambda B, but lambda is constant, it will get out. And in this case, we'll have lambda A B plus mu is a scalar product, a scalar quantity, so this would be A C. So again, if we have lambda A, the inner product with mu, again, lambda and mu are scalars, and here we have B divided by C. So this will give us the complex conjugate of A multiplied by the inner product of A over C, or vector A over C, plus the complex conjugate of vector A divided by vector C. So this is property 1, this is 2, this is 3, this is 4. Again, inner product of lambda A and mu B is just the complex conjugate of lambda multiplied by mu AB. So those just the properties of the inner products of two vectors in n-dimensional vector space. So let's talk about the orthogonal vector spaces. So if you have orthogonal vectors, vector A, the inner product with vector B, and those two vectors are orthogonal, what do you expect the inner product will be? Like in three-dimensional vector space, if you have two vectors are orthogonal, orthogonal mean perpendicular to each other, what's the inner product or the dot product? 0. So same here. Again, we will define the norm of vector A as we stated previously. Vector A can be a vector, can be matrix, can be function. So this is the way how you get the norm. And in n-dimensional vector space, usually we write the norm as two straight lines in each side. So in 3 dimension, this is what? Just one in 3 dimension real vector space. We write it as the amplitude of A. But because we are talking now about n-dimensional vector space, and instead of we say this is amplitude of vector, we call it this is the norm of the vector. The vector here might be function, might be an array, might be anything else. So the norm here is just equal to the inner product of A with itself to the power of 1/2. And this, in 3-dimensional vector space, when you get the amplitude of a vector, what you will do? So it is the square root of, so it is exactly the same. A inner product with A to the power of 1/2. In 3 dimension, it is the same. So if we assume that we have orthogonal basis vector, A1, A2, AN. So in three-dimensional vector space, what are the orthogonal basis vectors? IJK in 3 dimension. So if we are talking about n dimension and we define orthogonal basis vector, they will be E1 hat, E2 hat, E3 hat, and usually they will be orthonormal. So they will be orthogonal and they will be unity. They will be orthogonal and they will be unity. Usually we will define E, I, the inner product of EI and EJ as delta IJ, where delta IJ is the Kronecker delta function. How many of you heard about the Kronecker delta function? Yeah, so this is and it is equal to, when I equal to j, it's equal to 1, and it is equal to 0 when I is not equal to j. So far, do you have any questions? So we can represent any vector in the vector space, n-dimensional vector space, vector A, as summation from I equal to 1 to n of AI, which is a scalar quantity, multiplied by AI hat, or if we have vector B, also we can write it as same BI in the direction of AI. So AI and BI will be what? The components of the vector in the direction of what? The orthonormal basis. Those are components of vectors A and B in direction of AI. So if we just get the inner product of AJ and the vector A, this will give us summation of from I equal to 1 to n of AJ and AI. Then we can take AI as a constant, we take it outside. So this will give us summation of I equal to 1 to n AI, and this will be the inner product of AI, AJ, EI. And what's this? So this is the Kronecker delta function. Yes? So whenever I and j are equal, it will be 1, and whenever I is not equal to j, it will be 0. So I will be left with I equal to j. This is the only case, I equal to j, and in this case I will be left I will remove the summation sign, and I will be left with 1, and I will be j, so I will be left with aj. What does it mean? Again, the projection of A in the direction of what? Ej. It's like the three-dimensional vector spaces. It's the projection of A in the direction of, let's say, X, or A in the projection of direction of Y or Z in three-dimensional vector space. So how we will evaluate the inner product of two vectors? This will be the first vector. I will decompose it as E1 in the direction of E1, E2 in the direction of E2, up to En, An. And this is the inner product with B1, E1, B2, E2, Bn, En. Then what you will do is just, you will do the normal multiplication. Yes? So you will do A1, E1 by A1, B1, E1. Yes? And then A1, E1 by B2, E2, and so on. So we will collect all the ones, A1, B1, 2s, A2, B2, A3, B3, and so on in one single direction here, or place. So this will end up equal to the summation from I equal to 1 to N of AI, BI, and because you get from the properties that we just described, you get the A out, so it will be AI, the complex conjugate, multiplied by EI and EI, and then we will have I equal to 1 to N, and J equal to 1 to N, and J does not equal to I, because we already took the J equal to I here, of AI, BJ, EI, EJ. So this term is equal to what? 0. Why? I cannot be J. So this will be equal to 0, and you will end up with the summation, and this term is equal to 1. So this will be just the complex conjugate of AI multiplied by BI, I equal to 1 to N. So if the components of the vector, for example, A, are just real number, so the complex conjugate of a real number will be the same real number. If the component is 3, what's the complex conjugate of 3? 3. So in this case, the complex conjugate will be the same as the number itself. So it will be exactly the same like in three-dimensional vector space. When you have the multiplication of dot product of A, B, so it will be what? A1, B1 plus A2, B2 plus A3, B3. So exactly the same like here. And because in vector space, three-dimensional real vector space, the components of the vector are just scalar. They are not complex. Yes? So in this case, the complex conjugate will be the same number. You will end up with A1, B1 plus A2, B2 plus A3, B3. So we'll give just, without proof, we'll give some useful inequalities. first one is Schwarz inequality. And the Schwarz inequality just said that the inner product of A with B is less than or equal the norm of A multiplied by the norm of B. The second inequality is called triangle inequality. And it states that the summation of two vectors, the norm of the summation of two vectors is less than or equal the norm of both vectors. There is Bessel inequality, and it states that the norm square of vector A is greater than or equal to the summation of the projection of vector A in the direction of EI. All square. And the last one, just the parallelogram inequality. And it states the norm of the summation of A and B plus the norm of the difference between A and B square is equal to 2 norm of A square plus norm of B square. So now we'll shift gears and we'll start a nicer and more appealing topic, which has also correlation to the linear vector spaces, but it's a little bit easier to handle. So we'll be talking about matrices. And I think all of you took matrices in maybe high school or so. Yes? Or not? It's kind of? Okay, because in my time we took extensive matrices in second year high school or something like this. We took differential equation in the last year of high school. So the matrix is just a collection or array, rectangular array of numbers. Usually you can write it as A equal to, sometimes people will give it this bracket, or sometimes people will give it those parentheses. So whatever you want. So A1, 1. So the first one is the row number. So row number 1, and the second one is the column number. So A11, row 1, column 1, A should be 1, 2, row 1, column 2, up to A, row 1, nth column, A21, A22, up to A2N. And here, this will be M1, AM2, up to AMN. So we will call it M n by n matrix. M by n matrix. Thank you. So the the components or elements of the matrix A, Ij, we write it as AI J, where I goes from 1 to n and J goes from 1 to m. There is lots of flavor for the matrices. So we have column, matrix, and we have row matrix. The column matrix will be usually A1, A2, A3 up to AN, and the row matrix will be A1, A2, A3, AN. So usually we do not write here we do not write the what? The column number, because it is just one column. So this should be what? A11, A21, A31, AM or N1. Here we do not write the row number. So this should be what? A11. Yes, and this should be A12, A13 up to A1N. But we do not write it. So we'll define the transpose of a matrix. Usually give it capital T. And all what you will do, just rotate matrix A so that, so actually rotate rows of matrix A clockwise so that rows become column, and of course columns will become also rows. So if we have let's say A, B, C, D, E, F, G, H, I. So if I want to do the transpose, all what I will do is I will come to this one and I will rotate it like this until it became a column. So A, B, C. Come to this one, rotate it. So this will be D, E, F, and then I will come to this one and rotate it clockwise. So this will be G, H, I. Again, all rows became column. And look at the column now. A, D, G. A, D, G became a row. B, E, H. B, E, H become the second row, and CFI, the third column, becomes CFI, the third row. Did you understand how the transpose is done? So what about symmetric matrix? The symmetric matrix is defined as a matrix that's equal to its transpose. So if the matrix is equal to its transpose, we call this a symmetric matrix. And of course, Aij will be equal to Aji. Give an example. A matrix A equal to 1, 7, 3, 7, 4 minus 5, 3 minus 5, 6. So when you do the transpose, this will be what? You rotate it, so it will be 173. Oh, here it is. Then this one will be 7, 4 minus 5. And the last one will be 3 minus 5, 6. So it is exactly the same. So when you rotate the matrix, you make the transpose, the matrix will be exactly the same like its transpose. Do you understand? Any questions? So there is another types of matrices similar to the symmetric matrices, and we call it skew symmetric matrices. Skew symmetric. The skew symmetric is unlike the symmetric matrix, and the skew symmetric will have A transpose equal to negative A. So if you take the transpose of the function, will be negative, or of the matrix will be negative of the matrix itself. So we can give an example here. A is equal to 0, 2, negative 1, negative 2, 0, negative 4, 1, 4, 0. What's A transpose? 0, 2, negative 1, negative 2, 0, negative 4, 1, 4, 0. What's the relation between A and A transpose? Negative. So A equal to A transpose. And in this case, A Ij is equal to negative A Ji. There is the triangular matrices, and the triangular matrix, it's a square matrix. Square matrix means that M equal to N. If you have 3 by 3, 2 by 2, 4 by 4, 5 by 5, 8 by 8, billion by billion, this is called square matrix. So for a square matrix, if you have the elements in the matrix like this, 1, 4, 2, 0, 3, 4, 0, 0, 1. This is called the diagonal. This is diagonal. Okay? The diagonal of the matrix. If you have elements above the diagonal, so this is called triangular matrix. If you have elements below the diagonal but you do not have elements above the diagonal, again it's called triangular matrix. But this one, because all the diagonal is in the upper part of the diagonal, all the elements in the upper parts above the diagonal, we call it upper diagonal matrix. Why? Because all elements are above the diagonal, they are not equal to 0, but the element below the diagonal are equal to 0. So maybe we will have 1 0 1 0 here, but there is elements above the diagonal other than, even if it is one element other than 0. So this is called upper diagonal matrix. The lower diagonal matrix will be something like 1 0 0 2 8 0 4 9 7, and we call it lower diagonal matrix. Usually you call it LDM, and here you call it ADM, upper diagonal and lower diagonal. Do you have any questions? There is also diagonal matrix. And it has the form A, B, C, 0, 0, 0, 0, 0. So this is the diagonal matrix. So the other one is triangular matrix, and this is the diagonal matrix. Diagonal matrix, only the diagonal has elements, everywhere else is 0. Triangular matrix, it's like a triangle. Because look at this, this is the diagonal, this and this. So it's a upper triangle. And the other one is lower triangle. There is the identity matrix. So the identity matrix is nothing more than the diagonal matrix, but all elements are equal to 1 in the diagonal. So it's a diagonal matrix with all elements in the diagonal equal to 1. And this diagonal will give it the special letter I. So, and it has the property that if you multiply A with the unit matrix, will always give you the same A. There is also the null matrix. And from the name, it is the matrix all zeros. And so on. Matrix with 1 row and 1 column, like this. So let's jump forward to matrix multiplication, how we will multiply matrices. So let's look at basic matrix algebra. Let's look for addition first. So if we have A plus B equal to C, matrix A plus matrix B equal to matrix C, you will add all the corresponding elements in each matrix. First of all, we have to have the 3 matrices will equal to the same dimension. You cannot add 3 by 3 to 2 by 2. You cannot add it. You cannot add 3 by 3 to a column or a vector matrix. You have to have the same dimension. So you have to have same dimension, and then you will add same dimension, and then you will add Aij plus Bij and this will give you Cij. If we look for an example, for example, 1, 2, 3, 4, 5, 6, 7, 8, 9, plus, if you add to this, 10, 11, 12, 13, 14, 15, 16, 17, 18. If you will add the corresponding numbers, so 10 plus 1 is 11, 2 plus 11 is just 13, and so on, 15, 17, 19, 21, 23, 25, and 27. This is just for addition. Equality. So if we have two matrices A and B, and if they are equal, so first of all they have to be same size. What else? I will equate the corresponding elements again. So Aij will be equal to Bij. What about multiplication? By a constant. So if we have matrix B and multiplied by lambda, it will give us a matrix A, where A and B also same size. And in this case, Aij will be just lambda multiplied by Bij. The transpose of alpha, which is a constant, multiplied by matrix A plus matrix B, will be just the same constant alpha multiplied by the transpose of matrix A plus alpha multiplied by the transpose of matrix B. Did you have any question? Do you think the material is difficult? Easy? How many again took matrices before? So the majority of you, except one or two. Did you find the material difficult? Okay. So let's move to matrix multiplication. And usually all the students will do mistakes in matrix multiplication. You have to memorize how it goes. So matrix multiplication. So if we have a matrix A and a matrix B multiplied, A multiplied by B, it will give us matrix C. There is certain condition that has to be fulfilled, or have to be fulfilled. The first one is, if this is M by N, the matrix is M by N, and this matrix should be N by L. So those should be same. This should be the same. So this is the number of column of A should be equal to the number of rows of B. Number of columns of A should equal number of rows of B. And the result will be the matrix C of the remaining M cross L. And usually how we will proceed? We'll proceed as follows. The elements of the matrix C, Ij, will be just the summation of Aik, the element Aik, multiplied by the element Bkj. So say Ij. So what you will do, you will run this from k equal to 1 up to the number of column or number of rows, because they are equal in this case. So let's give an example. A equal to 1, 0, 2, minus 1, 3, 1, and B equal to 3, 1, 2, 1, 1, 0. Let's look at the condition here for the matrix multiplication. So this is what? So 2 by 3. 2 rows by 3 columns. And this is 3 by 2. Are they equal? So always look for the last one and the first one. Are they equal? Yes. So we can multiply those two matrices. Then the multiplication will be performed as follows. C equal to, we'll do we will run it for, the summation here is ran for what? For the first Aik multiplied by Bkj, yes? So it will be, we will multiply the first row by what? By first column. And this will give us the first element. First row by first column. Yes? So you will multiply A11 with A11, B11. So A11 by B11. Then you will add A12 by B21. So it will be like 1, which is this one, multiplied by 3, plus 0 multiplied by 2, 0 multiplied by 2, plus 2 multiplied by 1. And this is the first element, 1, 1. Yes? What is 1, 2? 1, 2 will come from 1, yes, and second column, the first row and second column. So I will multiply all this row by this second column. So this will be what? 1 multiplied by 1 plus 0 multiplied by plus 2 multiplied by 0. Again, I will do exactly the same, but for the second row. So it will be negative 1 multiplied by 3, negative 1 multiplied by 3, and then 3 multiplied by what? 2, and then 1 multiplied by what? If you look, you will notice that I have the same, which is the column. Yes? Then here I will multiply negative 1 multiplied by 1, and 3 multiplied by 1, then 1 multiplied by 0. Same, 0, 1, 1. If you do this, you will get to C equal to 5, 1, 4, 2. So this is how we will multiply matrices. So I will stop here, and next time we will continue the rest of the matrices.